So today we want to give you the first out of probably many deep dives into the core of what makes our planets tick and about the planet creation. And this is tech that is developed here mainly in Frankfurt by Marco, Sasha, Carsten, of course. Basically with the Homestead demo for CitizenCon, a practical test case of what we call the V2 planet tech, which is, we are already basically at V3 now. So we kind of needed to say at one point, that is it for the demo. So we have a couple more features already in progress. And the Homestead demo, of course, was not just made because of our love of giant space worms, but also to have engineers and artists work on something that is basically a substantial test case so that we can mature our tools, our planet editor, or what we call it, the plan ad, and to basically arrive at something where the usability has grown into a mature tool set, but also the feature set, of course, with the massive object distribution, the vegetation, ecosystem painting, and terrain height map. Working with our environment artist Pascal on the ecosystems themselves, which in the case of Homestead were actually only 5 distinct ones. And my job on Homestead was as visual director, and for that I basically initialized the lighting and mood and overall feel of this, and then also worked with our environment artist Pascal on the ecosystems themselves. And I basically also every day a couple of hours spent with Marco, Sasha and Carsten on the toolset itself.
Hello, we are going to talk about planets today. Thanks to everyone on the Star Citizen subreddit and the CIG community forums for your positive feedback. We really appreciate it. Initially, we were not planning to have seamless transition from space to planets into Star Citizen. Around September, we started rewriting from scratch the CryEngine terrain system. Here you can see my first experiment of a procedural planet without any atmosphere at the end of October 2015. Then this is our first test with atmosphere in November. Carsten Wenzel has been working on the atmospherics in clouds as well as a number of other engine features. And here is our first public update at the end of 2015 showing the first Delamar planet version. It was mostly procedurally based, but was already integrated into the editor, so you could place landing zones on top of the planet. In February 2016, we had the first man working on the planet. At this stage, we still did not have ground details, and we still had many precision issues, as you can see in the video. So during March and April, we made a lot of progress. We can see more details when zooming into the planet, and this is a video of the first buggy driving on the planet's surface. At this stage, the planets were mostly procedural, and even though we were getting good results, it was becoming difficult to really customize the planets.
There was no diversity in the planets. It was either a big rocky planet, or a jungle planet, or a desert planet, but there was no variation in the ecosystems on this planet. And with V2, this changed. We introduced something new, which we call ecosystems. So when we talk about ecosystems, what we mean is basically, you can think of it as kind of a level of its own. It's a piece of terrain, and it covers about 4 or 8 square kilometers, you could say. And each ecosystem contains many, many different kinds of assets, which are created by the artists. Part of it is the terrain itself, like the information that defines how the terrain looks. Is it mountains, or do we have dunes, or do we have plateaus or canyons, and all this type of stuff. Then additionally to that, of course, you need all the ground textures that make up the surface of the terrain. Do you have like rocky ground or grassy ground and this type of stuff? And then on top of that, of course, you also need assets, all kinds of assets that need to be scattered in a procedural way. This cannot be done by hand if you think on a global scale. So this is all of these things come into the ecosystem. And for this, Sasha Hober developed their own editor for the engine. And within this editor, we basically, all this information is accumulated and tweaked. We tweak the height of the mountains and where which texture belongs and which assets belong together on which surface, and all this type of stuff comes together in the planet editor in the engine. And once all these ecosystems are done, you can basically take your planet, which is more or less gray at the moment, and just pick some of these ecosystems and paint them over the planet. And this is basically how the terrain is generated in the end. Of course, when this is generated, you want to make sense of it. You want to have ridge lines of mountains, and then behind you want to have some hills, and that goes into grassy lands or desert or whatever.
So, at CitizenCon 2016, we were supporting spherical terrain, seamless transition, runtime generation at 60 frames per second without any pre-processing, unrestricted view distance and planetary scale, plus different ecosystems, and the first version of procedural vegetation, as well as hardware tessellation and per pixel displacement. Going back in time a bit before Gamescom, here is a test showing how Pascal had quickly put together a Mars-looking planet, using a few ecosystems and changing some parameters like atmosphere colors and so on. So with just a few ecosystems and painting them on the planet through the Planet Editor, we can create many different types of environments and planet. Here I'm showing a bit of our work in progress features. One of the next steps for us is improving the procedural vegetation placement and object distribution. In this video clip, you can see trees and grass being rendered through the zone system, which Chris Bolt is going to talk about in a bit. So here you can see in this last video another work in progress feature, a rotating planet. The planet is actually rotating extremely fast, but at this scale, looks like it's not moving. But if you get very close, on top of this large static control tower, which is not moving, we can see the planet rotating very fast. Another interesting thing to notice is the ocean, which was worked on by Anis, one of our new hires in Frankfurt. The ocean is reusing the planet terrain patches with different displacement. This way we're getting adaptive subdivision computations for free, and we don't even need any extra geometry, memory usage for the ocean.
The original ocean was also just a flat terrain piece, more or less. And of course, for the planet, we also needed this to be a spherical object. And this feature made it in. You can see that we have proper waves, there's vertex animation, it's nicely tessellated, the shading is working. Anis has really put a lot of work into it. And the next feature would be the clouds. The clouds are still in a very early stage. Carsten Wenzel is putting a lot of work into it, doing a lot of research, but you can already see some realistic behavior. You can see they are casting shadows, there are different thicknesses to them in certain areas. So there's less light penetrating. And speaking of light, one thing that also changed quite a bit is the sun. Because this is a spherical object, you have different kinds of lighting all over the planet. So you cannot just simply say, okay, for this planet, I want to have daylight. I want things, whatever is happening on the planet, to take place in sunset. Because depending on where you are on the planet, you have different lighting situations. And all this is now implemented depending on where you are. The atmospherics generate different effects. At sunset, obviously, everything turns red. And during daylight, you have blue bounce light from the sky and all this type of stuff.
Hello everyone, I would like to talk to you about the changes we did to our core technology, which allowed us to implement the planets as you have seen them during CitizenCon. One of the first components we changed was the job system. This system is responsible to distribute work, which must be done to compute a frame in a video game over multiple CPUs. This work is called jobs in our engine. The old approach was applicable for perhaps 3,000 to 5,000 jobs per frame, whereas the new one we can handle a very larger armor. This was realized mainly by utilizing the inherent parallelism of games, which is basically the smart way of saying that we have always more than one object to update. Furthermore, we changed the job system to better communicate with the operating system to allow for better usage of the available resources. We then built the zone system, which is a spatial object management system. Such a system is responsible to allow for an efficient way to query objects based on spatial properties, for example, finding objects visible inside a camera or overlapping with a box. This system initially replaced the old octave-based culling approach and is now used to store all kinds of objects within the world space position. This system had two important characteristics. Being efficient, the system should scale well. We already have over 200,000 vendor-able objects present in Crusader. This is realized by ensuring that we use efficient data structures and use a processing layout which maps well to multiple cores with the help of the job system. Then the system should cope very efficiently with large clusters of simultaneous moving objects. Here we use a novel approach of using multiple reference frames. The regular approach used in games is to store objects in a single coordinate system, the so-called world space. This world space position is then sent to the GPU as 32-bit coordinates and projected to the screen with a projection matrix. For Star Citizen, we cannot use this approach due to two reasons. The GPU can only process 32-bit floating point positions efficiently, but we need 64-bit positions for our large game world. We want to move kilometer-long spaceships and planets through space. In the old approach, this would mean updating the positions of all objects on, say, ships or planets, which is not possible in real time. So we did something else. At the highest level, we organized our world in a 64-bit position universe coordinate system. To render the object stored in it, we compute a camera relative position before we send the data to the GPU. This allows us to keep the whole world as one coordinate system by using the more efficient 32-bit position on GPU. To move objects around, we use multiple zones. A zone is its own coordinate system and hosts all objects which move together, like a spaceship or a planet. With this design, we can move an arbitrary large number of objects by just moving around the pivot of the coordinate system. Culling in such a system is implemented by converting the tested against objects into the zone space. This sums up the technologies we had to advance for our goal of a living universe. Thank you.